doing a special relativity. I'm going to give it 1 minute. Okay, see the number of students just doubled. See, there are signs of other students, but they're not here yet. Oh, serious, guys. So my apology for not being here on Sunday. I just could not move it on. And okay, basically this is the last time we meet in person before Passover, because on Sunday I will not be here. But it doesn't mean you're not going to have a lecture. There will be a tutorial with Akshay on Sunday. I will give you the next problem set today, but it will be for after Passover. So, right, there's supposed to be a lecture on Sunday. So again, it will not be with me, it will be with Akshay, because I'll be here. Then there is a 1.5, actually more than 1.5, basically 2 weeks that we're going to miss lectures. The next lecture is going to be the 24th of April, something like that. Right, so. Okay, so let's do a quick recap. What we did. Okay. At 12 there was 1 student, and 12 was 2, there are 6 students. Try to be on time. So we spoke about tensors last time. I introduced you to the concept of tensor. And I said that tensors are multilinear map from tensor T. T of, we say, rank KL of tensor rank KL is a what? Is a multilinear map from what?
A collection of K dual vectors.
Yeah. K from a collection of K dual vectors and L vectors to R. And we write it as T mu1 mu K mu1 mu L. As usual, the order matters a lot, right? So you cannot just switch them. K upper indexes, L lower indexes, and transformation law, each index according to the way it is. If it's an upper index, like a vector; if it's a lower index, like a covector, right? So we introduced a few tensors that you know. So one tensor which you know of is the metric tensor, eta mu nu. This is a tensor of metric tensor. This is a 0,2 rank tensor. It's very important. We use this tensor and the inverse tensor to raise and lower indices. Only these tensors, right? And when this tensor acts on 2 vectors, eta of v and w, we call that
Inner product.
It's the inner product. This is eta mu nu, v mu, w nu. Or we simply call it v dot w. We know how it looks like. And the inner product of a vector with itself is the norm. Eta is v, is the norm of v. And we said that eta, unlike what you used to from Euclidean space, the norm of a vector can be both positive and negative and 0, and the vector does not have to be 0. Right, so we have eta mu nu v nu v nu can be either smaller than 0, equal to 0, or greater than 0. If it's smaller than 0,
Time.
call it time-like. If it's greater than 0, call it space-like. If it's equal to 0, call it light-like, or none. Why is that? Because light, vectors that describe light, is always a null vector. Okay. And we introduced a few other tensors very briefly. So we introduced the Kronecker tensor, the Kronecker care delta. I told you this is the only tensor that I'm writing with one index on top of the other and not reserving spaces. Which one? Only one, that's the exception. We introduced the inverse metric and a new inverse metric. Inverse metric. Third tensor that we introduced. So at mu at rho is equal to at rho mu at mu is equal to delta. What's the upper and what the lower index?
Mu upper, lower.
Right, you remember that every index that appears twice in an equation on the same side of an equation, it is new, is known as a dummy index, and really we're summing over it. Then indexes that do not appear twice on the same side of the equation has to appear the same, either its upper or lower indexes on the other side of the equation. If you don't get it, you're doing something very wrong. Okay. Then the last tensor we introduced was the Levi-Civita tensor. Epsilon mu sigma, which was what?
1 for even permutation.
So plus 1 for even permutation of 0, 1, 2, 3, minus 1 is an odd permutation, and 0 otherwise. You've seen that before, right?
Yeah.
Maybe not in 4 dimensions, but it doesn't matter. Same idea is the same idea. Then we say, okay, we can use the metric and the inverse to raise and lower indices, right? So I can write down T alpha beta gamma delta times eta mu gamma is equal to what? Yeah. What's the first index?
Yeah.
The first index?
Alpha.
Alpha, upper or lower?
Upper.
Upper. What's the second index?
Beta.
Beta, upper or lower? Upper. What's the third index? Somebody else?
Mu.
Mu what?
Upper.
Upper. Sum over gamma here, right? So it's an upper mu.
And delta.
And the fourth index?
Delta.
Delta, lower. At the end of the day, it's very simple. There's only one thing you can do with that. Okay? Remember, you always have to have the same number of upper indexes and lower indexes. Here and here. Right? No need to repeat it any further. So, if I do eta mu nu v nu, what is that equal to?
V mu
Lower
index.
Lower index, right? So I turn a vector into a covector. Okay? Again, in 3D Euclidean space, you don't see any difference. In 3D Euclidean space, this is simply the identity matrix. But here we have 4-dimensional Minkowski space, or at least minus. Right? Yeah. So because of this minus, there is a difference. They're not the same. And conceptually speaking, As I said, they don't live in the same world. They don't live in the same space. This lives in TP. This lives in TP star. They cannot merge together in a way, right? They cannot be added like you can do with vectors. Okay. And then the last thing I said, we said we can do contraction with tensors. Contraction. What is a contraction?
Summation over all of the indices.
Right. So if I have T, mu and mu rho sigma nu, that is equal to what?
T mu.
It's a different tensor, so I'm writing it with a different name. S.
That's with mu.
First index.
Mu.
U. Upper or lower?
Upper.
Upper. Second index.
Then rho.
Rho. Upper or lower?
Upper.
Upper. Somebody else? Third index.
Alpha lower.
It's a sigma. There's no alpha.
Oh, sigma, yeah. Okay.
Sigma. Lower. I told you. Refresh your knowledge of Greek alphabets because we're going to use them. Okay. Fine.
May I ask a question?
Yes.
When we have, for example, with a metric tensor,
Yes.
it has both two lower or two upper indexes, and the first one corresponds to row, and the second one to the column. The same logic works with tensors which have upper and lower indexes.
Yeah. It's okay. This is a way of presentation for ease of you to think of it. But the tensor itself, I mean, I cannot write it as a matrix if I have more than two indexes. If I have one index, I can write it as a row vector or column vector. If I have two indexes, I can write it as a matrix.
Okay.
If I have more than two indices, then I cannot write it in a simple way like that. But the tensor as an abstract object still exists. It doesn't care how I write it or not. It's still there. And the way it operates on other tensors or other vectors is well defined mathematically. This is a very easy for calculation. For example, if you're using it in a computer, right? You want to write the code that calculates some components of a tensor, you can use it like that, very easy.
Mm-hmm.
But the matrix representation is useful for us for simple tensors such as matrix, or any tensor that is two-dimensional or two-index tensors.
But with three indexes, we can also imagine.
I can, but it's going to be very cumbersome. Basically, I can write it down like the only way I can have is just to make a whole list of, if I have, let's say I have a tensor R mu rho, then I can simply write a list of mu rho 0 0 0 0 0 1 0 0 2, and that is the tensor T R. Mu rho, what is the value that it gets? The tensors can have more than three indexes. There is no simple way of the exact definition of a tensor is that. That's a definition. This is a representation. So make a separation between what it is and how do we represent it. That's for us because it's easier for us to think of it like that.
Visual representation of we would have a third index. It would be writing inside and going out of the board. Right?
Yeah, it's like a box if you want.
Yeah.
But then what are you going to do if I'm going to add up a fourth index?
Yeah, no, I'm just the visual.
Yeah, you can envision it like that, but I think it becomes less and less useful when you go to. So if it's a vector or a covector, it's useful to think of it in terms of row vector and column vectors. Column vector, row. If it's a 0,2 or 2,0 tensor, it makes sense to think of it in terms of matrix. More than that, the only correct way to do it is thinking in terms of a list, like a table. Otherwise, you'll see, because not now, but after the holiday, we're going to speak about objects that are not tensors. When you see it's going to get more messy. Right now, we are doing the simple things. Don't worry, we'll get you through everything. Okay, after discussing some of tensors, we move to speak about kinematics. So this is the special relativity that you're familiar with. And I promised you that we can do everything you learned in first year in half an hour after we are familiar with this notation. And I wasn't joking. I spend a lot of time doing the math, and then everything else comes quite easily. Now I should mention that obviously tensors are not, the use of tensors is not limited to relativity. There are other courses which you might have seen them, such as E&M, and our electric fields. You might have spoken about the stress energy tensor or the Faraday tensor, you might have seen that. It's very useful when it comes to transforming electric field and magnetic field between one frame and another. In fact, that's how this Lorentz transformation began, when you think of it. So I don't know if you've seen that or not. You might have not seen that. Generally, this is a place where sometimes you see that. Other places that you see that, even in condensed matter, of course, you can't see it, you don't have to. Yeah, conductivity tensor is something that you see in plasma, you see that. So the concept of tensors is not unique here. Of course, in quantum field theory, I already mentioned to you that the same metric tensor is there after a minus sign. So it's all there. It's a very useful tool after you get used to it. Like the same way that vectors are very useful tools. And we're going to see exactly why we need vectors. So now we talk about kinematics. So we start by this concept of force velocity, acceleration, for force. And I actually started by introducing to you the concept of the world line. We said that in Newtonian mechanics, we used to think of the problem in terms of the coordinates of an object as they change with time. Have two balls, they move, say you have two stars, they move around each other, so you can specify the location in space, x, y, z as a function of t. In special relativity, it's not very useful, because t is a coordinate by itself, and these are all interconnected with each other via the metric. So the easiest way to think of it is in terms of, we introduce the thing which is called world line. So we take all the spatial coordinates and put them on the x-axis, and on the y-axis we put the time. And to make sure they have the same units, we really multiply it by c. At this stage you should be aware that c is of course equal to 1. Let's still keep it here. And then I can speak about my world line. So I put all my spatial parts here and my time here, and of course I move. This is called my world line. Now, if I was a photon, how would I move? 45 degrees. So this spherical shape, you might see in these small cartoons. We'll get to them in the future. You'll see that, right? Now I'm confined. Basically, my world line is confined within this cone. This is called the light cone. Why? If I want to cross this light cone, what do I need to do? I need to travel faster than the speed of light, and I can do. So if there's something that does something like that, that means that I have to travel faster than light. So there are hypothetical particles that do it, but we're never seen in the lab. So that runs into various troubles, and I told you that this is the origin of This is one of the bases of quantum field theory, why this theory was developed to avoid these problems. Exactly this problem that in quantum mechanics you can have in principle various phenomena that seems like they travel faster than light, so obviously it cannot be because that contradicts the Michelson and Morley experiment. So that's why this whole concept was invented, to avoid it. Right. Okay. Now, so how do I describe the motion along the world line? So if this is, yeah, exactly. So I that's what I can do. I can just specify some parameter along the world line. It can be anything, but most useful is the proper time tau, and then I just say x mu as a function of tau. Right? X mu or the coordinates, time x, y, and z. Right? It doesn't have to be tau, but it's just easy to use tau. Right? And then once I did that, then the rest is pretty much follows. Then I can define the 4 velocity. Right? U mu is dx mu over the tau. Nothing much I can do, and then I showed you that this ends up with u0 is just a gamma c, and ui is just a gamma beta I c. So if you want to know what is your regular velocity, just divide ui divided by u0. That's why I use u, capital E. What is the norm of the 4 velocity? Minus
1.
So u squared norm. U squared is u mu. Eta mu, and we show this is equal to minus c squared. So the 4 velocity is always constant. Norm. Yes.
Proper time is basically the time in reference frame of the particle.
It doesn't matter. Yes, but it doesn't matter, right? That is concerned. The thing.
Proper time is conserved.
Yes, because we said it's derived from the interval, which is concerned. But yes, basically this is the time as measured in the rest of the part. If this is taken from the interval, it will be conserved. Variant, basically. So that was what will be the 4 acceleration?
The u mu to the
Second derivative.
The only thing we can do, basically. There's nothing else we can do. So a mu is d u mu over the time. That's a nice thing. Once you get that, you're very restricted. There's nothing you can do. What's going to be the full force? Or half mu, that's the relativistic equivalent of Newton's second law of motion.
the derivative of the momentum with respect
Oh, wait,
to
not yet.
I'll
Didn't
multiply
define
by
the
m.
momentum. What is that?
Just multiply by m.
Yeah, m a mu. Yeah.
when
So
you write
m
in n, it's the rest mass?
Yeah.
Or not?
d u mu over the time. Didn't even define the rest masses. Yes. So this is called the constant here. This is called the particle's response. When the velocities are not relativistic, what is gamma?
1.
1, right? Beta approaches 0. So we get u0 is constant, is c, and ui is just the velocity. We retrieve back. So the next thing is the 4 momentum. So how am I going to define the 4 momentum?
mu.
Yeah. P mu is just m u mu or m dx mu. What is the norm of the form momentum? P squared.
E squared minus.
What?
There is an Einstein invariant.
P mu. And what?
E squared minus or plus.
No, from what is written on the board. I don't know what is E.
M squared is equal to
So it's a minus m squared c squared. And what is P0?
M gamma C.
Let's say gamma MC. And Pi?
Gamma and beta C.
Beta I.
Beta I.
So it's gamma, beta I, MC, which is gamma and Vi. So, in the limit of small velocities, in the non-relativistic limit, right, V much more than C, beta I much more than 1. What is gamma? Yeah, but if I do a Taylor expansion,
1 plus half beta squared.
yeah. So what is P0? Just plug it in here. I have an MC plus 1/2 beta squared is V over C squared, so it's a V squared M, V squared over C. And what is Pi? Just MVI, because I don't need the gamma, because then it will be third order. That's going to be MVI. Non-relativistic thing. What is that term?
That's the Newtonian.
This is the Newtonian momentum. Here we have P0, so what happens if we take P0 and multiply by C?
With the energy.
C P0 is C squared plus 1/2 M V squared in this limit. Plus, so V to the 4. What is that?
Newtonian.
What is the Newtonian kinetic energy, right? What is that?
Rest energy.
Where did it come from? Wasn't there? Beautiful, isn't it? Just use these definitions and voila! This term popped out. Just like that. This is the restless energy. I want you to appreciate it, right? Everybody, you've seen that when you were 3 years old. Einstein didn't know about this term. Didn't think of it. This was the way it was thought. Okay? You just wanted to go. There's only one way you can go here, pretty much. Once you define the x mu, right? U mu A mu, F mu, P mu. You just take the limit, and that's what you get. This term came out of nowhere, came out of the equation. Einstein basically got it for free. It's not clear if even, I don't think it even appeared in his 1905 paper. Only later on it appeared. Right? You get it for free. This, by the way, so I don't know if you know that, it's a very interesting story about the history of science. You know the great debaters in the 19th century. How old was the sun? How old is the sun?
5 billion years, 4.5 years.
4.5 billion years, yes. How do you know? You read it in Wikipedia. How do you know? So, end of 19th century, people didn't know. There was a debate. Might have heard of that, right? Between the two of the leading scientific figures. One was a physicist, you know who it was?
Yes, Kelvin and
Lord
Darwin.
Kelvin. Yeah, Lord Kelvin, right, the greatest physicist of his time. On the other hand,
Darwin.
was the great scientist of all times, which is Darwin. Right? And what was the claim? Kelvin tried to calculate how long the sun existed. He got a value which was a few millions of years. Because he could calculate the rate in which the sun radiates its energy. He thought how much chemical energy there could be inside, and that was what he got. Darwin was basing an argument on something completely different. He was looking at glaciers that move. And he estimated the time that it takes to reach the valleys would be much longer. It would be more than a few million years. I don't know what this value was exactly. And it was unsolved until this extra source of energy came in. This is the source of energy of the sun. Mass is converted into heat. So the sun loses some mass, nuclear processes, converts it into heat. That's what happened in any hydrogen bonds. Okay? And Einstein just got it for free from the equation. Now, because this term Cp0 is an energy term, and this is a momentum term, then this 4 vector is not called only 4 momentum, but it's also called energy momentum 4 vector. P mu, the other name of P mu is the energy momentum 4 vector. And then using that, right, gamma squared beta squared plus 1 is gamma squared. Right. So if we call P0 is E over C. From here, Cp0 has the units of energy. So P0 is E over C. From here, what do we have? Let's write it as Pi squared plus M squared C squared, all this by 1/2. Essentially that. Cool, isn't it? You've seen that before.
Yeah.
Why not? So we spend a few lectures speaking about tensors, and we got all the GR kinematics from it. Is it clear? Questions? No? Everything's clear? Sure. If you're being asked in the exam, you'll know what to do. That's the meaning of clear. What about massless particles? Massless particles. for massive particles, we know that always V, they must be traveling at a speed which is smaller than c. Right? No massive particle can travel at c. We are all limited to travel velocity smaller than c. But massless particles.
Travel exactly at C.
What?
They will travel exactly at
Yeah,
C.
they will travel at c. Massless particles travel at c. Can we use tau then? Let's say we have the photon travels in the x direction. Right, so x is equal to ct. Right? What about tau?
Well, tau will
Can
be-
I use tau as a parameter along the world line?
It have to be 0. So
It's always 0, right?
make no
Well, think of
sense
it
to-
for a second, right? How long it take light to travel from the sun to Earth? 8 minutes, right?
From
Yeah.
our
From our
perspective.
point of view. And if you're on a photon, how long it takes the photon to travel from the sun to us?
Immediately.
0. Right? From the photon perspective, it takes 0 time to reach us. Cool, isn't it? Right, so we cannot use tau. Right? If you use tau, because the tau is always 0. Tau is always 0. Okay? So we must use a different parameter. So the tau is always 0. So we must use a different parameter. Doesn't matter which one. Right? So I just call it lambda. So if I'm talking about a photon, just call it lambda. What is the 4 velocity? So 4 velocity would be u mu is just the x mu over the lambda. Whatever lambda is. Now it's a null vector. So what does it mean? What is u squared?
Zero.
0. I just said it takes 0 time for the photon to travel from us to, from the sun to us. Right? If there is no force, what's the equation of motion of a photon?
F mu equals 0.
Of course. So du over the lambda, 0. It's very simple. There's nothing else you can do here when you think of it for a second. What about the energy? Photons do carry energy.
Linear.
What? It's got nothing to do with the trajectories. It has to carry the energy associated with their frequency. Einstein himself showed that, right? So E H. Oh, sorry, H by one. Sorry. H. What is H?
Spark.
Spark. What is that?
What?
What? Planck dots. H. So we can, in principle, use that same equation here. Mass is equal to 0. Right? So we can write down pi, the momentum, is E over C, is h bar k. Okay, is a wave vector. So the photon for momentum P mu is h bar omega over c, h bar k. And p squared, p mu is pretty much covered everything we learned in first year. Special relativity in half an hour, I suppose. Questions? Okay, we cannot yet leave special relativity. There is one more thing which we need to do before we can leave it. That's something which you did not see before. We do have it. We have to have it. And that is called, okay, so this was about single particles. Okay? But life is not always so simple. Sometimes not only single particles, sometimes we have to deal with systems which contain many particles. And so that forces me to introduce to you a new tensor which, let me see. Did any of you hear about the stress energy tensor? Or the energy momentum tensor? That is a PT. Okay. Questions? Anyone?
I have a question about orthogonality in this Minkowski space.
The what?
Orthogonality.
Orthogonality, yes.
Yes. Looks like a 45 degrees angle. It's if we have this axis direction, so rotate by 45 degrees, every line compared to this 45 degrees is orthogonal. Right?
What do you mean orthogonal? Not sure I understand. This is a misleading. The orthogonality condition for a vector is what we define. Eta mu nu, v mu, v nu has to be equal to 0. V mu, w mu equal to 0. This is the orthogonality condition. This is, again, this is for us. This is for presentation. Makes you easy to think of things, or to visualize the motion of particles. Of course, I condensed all the spatial dimension into one line. But this is just for me. Doesn't mean that there are 3 dimensions here. X, Y, and Z. If I want to know if a vector is orthogonal to another vector, it just use the orthogonality condition. There is the abstract mathematical structure, and there is, these are visualizations to make it feel like you understand it better. There is no more than that. Okay. So yeah, for a photon, right? P is null vector, so you can take it. It's orthogonal to itself. Yes, which is fine. In Minkowski space, a vector can have a 0 norm without being 0. So you just, again, there is no analog to that in Euclidean space. So you cannot really, again, the physical intuition that I just gave it to you. If you're a photon, doesn't matter, you can travel from other galaxy, the other side of the universe, until you reach us. It can be billions of years. But from you as a photon, it doesn't take any time at all. Just from the time it was emitted to the time it was basically absorbed, right? Detected by any detector, which is your eye, for example, or a telescope, it doesn't matter, right? From the photon's point of view, if there was like a little dwarf sitting with the photon moving with it, it took 0 time. That's the physical meaning of that. Beyond that, it's you have to play with the mass until you feel comfortable with it. Okay. More questions? So, all good? So, what is it? Yeah. next I want to speak about is a many particle system. Actually, that's the. We'll see how much time we have. That's the last thing that we have to do on special relativity before we move to the general relativity. So we'll move the general relativity part, I guess, after the holiday. I won't start it now. I will give you a new problem set. Have in mind the last question has something which looks like geometry. You can easily, you don't really need geometry to solve. So you can simply solve. Many particle system. The energy momentum tensor. Another name is stress energy tensor. It's the same name. So the same name, it's the same tensor. So far, everything we did, and I guess everything you did in first year special relativity, correct me if I'm wrong, was treating single particles. Right? And when you have a single particle, it's enough to specify the form momentum, P mu, to give you the information you need about this particle. For a single particle, the form momentum, that's essentially what you need. But what if we have a system that's composed of many particles?
You mean Avogadro number?
Yes. Gas. Fluids. Then we need something which is a bit more complicated. And then we cannot use a single vector, we need a tensor. And we call this tensor T mu nu. T mu nu is the energy momentum tensor. We're going to derive it in a second. As you see, this is what is the rank of this tensor? 2, 0. Right? This is a tensor of rank 2, 0. Another thing about this tensor is that it is symmetric. So if you change indexes, you get the same result. And basically, this tensor tells us everything we need to know about the energy components of the system. So very crudely, T mu nu is the flux of form momentum P mu across constant x nu, roughly. T mu nu is the flux of form momentum P mu across a surface of constant x nu. So okay. What does it mean? Now let's do the business. So we first introduced the concept of fluid. In fact, in astrophysics and in general, in life, many things are fluid. In astrophysics, everything is fluid. Pretty much. What is a fluid?
Reacts to each other in general way.
And give me an example of a fluid. Water is a fluid. Well, it can be ice. Okay. let's be a little bit more, let's try to get slightly deeper. Is any collection of a particle considered a fluid?
No.
No. So what makes a fluid a fluid?
משמר את הנפח, we cannot compress it.
Actually, no, because a gas is compressible fluid. When you say in English fluids, that means both gases and liquids. So the gas in this room is also a fluid. And there is a compressible fluid and non-compressible fluid. So gas is a fluid. The sun is made of fluid. For me, it's a
So
fluid.
maybe
Actually, I can think of all the collections of stars in the galaxy as a fluid. It's not a bad assumption. I can think of all the galaxies in the world as a fluid. Okay.
so
what
maybe
is
it's
it?
fair to say that the particles are not well localized.
No, they're localized. Roughly. No, that's not the issue. I was looking for something else. I was looking. You also had the course in thermodynamics, right? So what would be a thermodynamical definition of a fluid? Maybe they didn't tell you that. What is thermodynamics about?
Oh, it's equilibrium. Exploring equilibrium state.
Okay, and what defines equilibrium state?
All the parameters, time independent, pressure, temperature.
Okay, oh, good. What are these? These are macroscopic parameters.
Yeah.
Right? So these are not. We cannot specify a temperature of a single particle. Right? Single particle, you can say what is the energy of the particle. But the temperature is something which is you can describe for a collection of particles. Right? You have some distribution, and overall you look at distribution. You say this distribution looks like a Maxwellian distribution, and that Maxwellian distribution I can associate a number, which I call this a temperature. Right? You know what I'm talking about.
Yeah.
So, fluid is a continuum of matter, a continuum of matter that is described by macroscopic quantities. Macroscopic quantities. Such as temperature, pressure, entropy, a few others. Viscosity, these are all macroscopic quantities that describe the fluid. Now, in fact, for me, that is too general. Right? We cannot use it per se. We can, but it's not going to be very useful. We need something which is a little bit more restrictive, which is perfect fluid. What is a perfect fluid? Did anybody talk to you any time about fluids in any of the courses you've ever taken? Okay, I mean thermodynamics should have mentioned that at least, I guess. Okay. When thermodynamics you speak, it's just a gas, right? It's a gas has some temperature. That's all about fluid contained gases. Okay. What is a perfect fluid?
Can neglect interactions within the system. No?
How you use your imagination. Other suggestions? Working perfect. Zero viscosity is one. Yeah, then you get in there. So there's more than a single definition of a perfect fluid. So no viscosity, that's not enough, by the way. We have no viscosity and no heat conduction. That would be, so that's why there's a definition of Schutz. If you go to the textbook by Schutz, that's the definition of perfect fluid. Fluid Schutz. no viscosity of fluid. Fluid with no viscosity. Viscosity. No heat conduction. But there is something which is, I thought was simpler. This to me it's simple. So they are equivalent. Which is what? Perfect fluid is a fluid that, if you sit in the rest frame of the fluid and you look around, it's isotropic. Okay. So that's a Weinberg. A fluid that is isotropic in its rest frame. Okay. You all with me? In fact, it's not difficult to show that these two are equivalent. Definition of perfect fluid, and in fact, when you think of it, what you did in thermodynamics is dealing with perfect fluids.
By absence of heat conduction,
Yeah, there's no heat conduction.
mean that, for example, CD is equal 0. Like in terms of heat capacity.
Heat capacity is something else. No heat conduction, there is no heat gradients inside. Sorry, yes. Heat capacity would be equal to 0, yes. Okay. So for us, what I'm going to derive now, for us this is enough to say that the perfect fluid is fully characterized by only two quantities, which are density and pressure. Okay. For us, a fluid that is characterized by only two quantities, density and pressure. Okay, these are all equivalent, of course. Yeah. Now, before we're going to derive the stress energy tensor for fluids, I'm going to take even a step back. I'm going to define dust. It's good timing, right? For Passover. What is a dust?
Zero pressure.
Zero pressure. Dust is a fluid with zero pressure, right? So it's a collection of particles that don't interact with each other, so they have zero pressure. Okay? So dust dust is a collection of particles, at rest with respect to each other. Or a perfect fluid with zero pressure. So if the dust particles are not moving with respect to each other, right, but they may be moving relative to me. Okay, so I can say that there is a velocity field, which is the same velocity for each one. Right, so we can define, say that there is a velocity field u mu. X defined in all space-time. Now we can define the number flux for vector. And mu is n times u mu. And number density of particles as measured in their rest frame. Now you get used to it because that's one of the things that I was confused at. So now what to see. So we talk about number density, various densities, right? There is a you have to be careful about what you speak. Density, right? Number of particles per unit volume. It's a number density. I can also speak of a mass density, right? How much mass is at the given volume. I can also speak of an energy density. If each particle carries an energy, then I can speak of how much energy is per unit volume. We can speak of a charge density, how much charge there is. Again, if each particle carries a charge, then there is. Right, they're all with me, so just don't get confused with it. So like the unit volume, and I can ask myself how many particles are in this unit volume.
But why should the number of particles change between reference systems? I mean, the unit of volume might shrink if you're moving really fast, but the distance between the particles also shrinks. The total number shouldn't change.
Total number is conserved, but the density, as you say, is changing. Right? The density is changing. Okay, because the volume changes. Of course, the total number of particles is invariant.
Yeah, but let's say in the rest frame of the particles, I don't know, 5 particles in a unit volume. Okay, and each one of them has a specific distance between them. And now I'm looking at a system which moves in 50% of the speed of light. So
Sure, right. Moving relative to them.
Yes, so the unit volume would shrink. In
The number of particles inside the unit volume will remain the same.
The number inside the unit
The
volume.
number will remain the same.
So the number density.
That's number density will change. That's why I say this is the number density in the rest frame.
Okay.
Yes.
If you're talking about density, you need to talk about the volume, right? So this is three-dimensional space always?
No, it's a density. Yeah, it's a density. Yes, so it's a three-dimensional. Okay. So from now, this is in the rest frame. So now in any arbitrary frame. So in arbitrary frame, in any frame that is moving, or this seems to be moving relative to that, in arbitrary frame, right. Let's say that n0 is the number density of particles. And I is the flux of particles in the xi direction. So in the frame in which the dust is at rest, right, what is the number flux for vector? The components. in the frame in which it is at rest.
It's small n and 0 and 0 in another.
Right. So in the frame in which it is at rest, the n mu is n 0 0 0. Yeah. Now let's say that all the particles have the same mass. So m, the rest mass of each particle. Right? So the energy density in the rest frame of the dust what is the energy density? This I denote by rho. So I use different n and n for number density and rho is for energy density. If I need charge instead, I have a rho c. Yeah. Rho, what is it? Yeah.
Small n times n c squared.
Right. Just n times m c squared. Right? M is similar to all particles. Same for. So this energy density obviously completely specifies the dust. This is in the rest frame of the dust. What will be the energy density in any other frame, not the rest frame? If I'm now moving in a spaceship and I'm seeing some dusty.
So just need to go up.
What? No. So you can think of n. Oh, don't think of it, right? This is the zeroth component of the 4 vector of the number flux. And mc squared is the zeroth component, right?
The energy
The
momentum vector.
energy momentum vector, 4 vector, right? So we can think of rho, zeroth component. So you can think of rho as a zeroth component of a more general tensor. Okay? And that exactly leads us to define P mu for dust to be P mu and mu, which, using the definition here, so just n, m, u mu, u mu. Or rho, u mu, u mu.
Actually, c squared.
Excuse me. So rho, this is the energy density in the rest frame. And the dust rest frame. Now, I don't know if you've seen that. Now we can start playing these games and write down all sorts of equations. Did you ever see equation of continuity, by the way? Yes?
Yeah.
Where did you see it?
משפט הרציפות.
Okay.
Dynamics.
In all kinds
All kinds of, yeah.
What?
Electromagnetic
Mechanical
yeah.
analytics.
Yeah,
For
also
example.
gravity.
Okay. So you did see it?
Yeah.
Cool. So I'm going to write it down in a very elegant way. The most elegant way that you've ever seen. How do I write the continuity equation?
Don't use
What? to shorten it. What is that? D mu and mu is D and mu over dx. Right? Let's see. In fact, it's not just a continuity equation, it's more than that. No, it's one equation. It's equal to 0. So, dn0 over dx0. So what is n0? U0, so I can write it down as d over dt of gamma n plus here d gamma n v or beta over dx is equal to 0.
Why don't you put
So I can write it d gamma n over dt plus gamma n v is equal to 0. Of course, in the limit where gamma is equal to 1, we get back continuity equation and return the limit. Cool, isn't it? You all with me? You follow what I'm doing here?
Can you explain why there is no minus before the t component?
Why should we rate equal?
The derivative.
dx mu, so x mu is ct. You're mixing with eta.
But when you're writing
X mu, right, is ct, x, y, z.
okay.
Right.
And dou mu.
Dou mu is dn mu over dx mu.
But if I want to write it as a hope vector, if I
Remember?
say
N mu is a vector.
okay.
X mu is a vector. This is a notation, we learned that.
Okay.
This is what it means. When I write it like that, d mu and mu is dn mu over dx mu. Since I have an upper index in the denominator, it becomes a lower index when I write it down with the derivative. It's notation. If you want, I can write this n mu comma mu. It's the same thing, right?
Does the notation mean that it's the sum of all the
Of course.
separate?
Of course, there's a sum. U is 0 to 3. That's why I have here the same equation. This is the 0 term, this is the x, y, z term. So this small notation that is equivalent exactly to that. Some of you don't look happy. I don't know why you look very happy. You all see the continuity equation, right? I just show you this is the continuity equation. This is called the covariant form of the continuity equation. And you see that it's much more elegant than the physical content is exactly the same as the physical content of the continuity equation you're familiar with. Only more general. This is true in any velocity. This is true also for relativistic fluids, not just for non-relativistic fluids, as you said.
But gamma is just a constant, right?
It's the Lorentz function. Yeah, I'm assuming that the fluid is moving at a constant velocity.
In that case, gamma, you can just divide by gamma, both sides, right? If it's constant.
In principle, well, actually, this is more general. Gamma doesn't even have to be constant. You're right. The fluid can change. You know, this equation you can think of it as derived from a river, right? You have a river, and there is you look at how much fluid is getting in the box, how much gets out. Yeah, so you're right. I'm sorry, gamma doesn't have to be constant. It can change with time and with space.
Because otherwise it's just
Yeah,
the same
right.
equation.
You're right. Otherwise, they don't do that. Yeah, but this is a more general. Sorry, my mistake. Okay. Very good. So now let's talk about fluids.
Can we go back for a second? I have a question about this pencil.
Yes.
V, it's velocity of the
U mu and u mu.
It's velocity, right? Or
Yeah, I just erased that. The dust is defined as a collection of particles that are at rest with respect to each other.
Yes.
But I can be in a frame in which the dust is at rest relative to me. Or I can be in any other frame. I can look at the dust in any frame, which is not necessarily at rest. So I can define a velocity field which is the same velocity u mu everywhere in space. Okay? So one way to think of it is, okay, let's say that there is some interstellar medium, some dust, and I'm traveling in the ship. Right? So of course I'm moving relative to the dust. I can think of it as, from my point of view, the dust is moving relative to me at some velocity u mu. The thing is, it's the same velocity everywhere, because the dust is at rest with respect to itself. So if I see one particle moving to me at some velocity u, then the other particle will move at exactly the same velocity. Yep. Okay. You're too busy with your cell phone, so I don't know if that's should speed up, so you should be. Okay, so now let's talk about fluids. So now I'm relaxing the assumption that of zero pressure. So now we talk about fluids. We still stick with perfect fluids. We're not going to do anything with no perfect fluids in this course. So we said perfect fluids, one way was isotropic in its rest frame. Right. So if it's isotropic in its rest frame, then automatically what does it tell us about T? It doesn't have any preferred direction. It has to be diagonal. T mu nu is diagonal. Because there is no net of flux of momentum through any boundary, basically. Okay. And more than that, all the spatial components, the non-zero has to be the same, because there is no preferred direction. Right? So no preferred direction. Preferred direction. And T11 is equal to T22 is equal to T33. So really we end up with only two independent components, T00 and Tii. So two independent components T00, Tii. So this we can call the energy density, rho, and this we can call the pressure. The same P as momentum, but there's no Pi, so you know it's a pressure. So, in its rest frame, you can write T mu nu to be rho P E P. That's in the rest frame. Not in any general frame. So in a general frame, for the dust, we had the T mu nu dust is rho u mu u nu. Right? Which is easily generalized from here, right? If P is equal to 0. So we can think of having P plus rho u mu u mu. And that will end up with what? The rest frame. P plus rho, and then everything else is a 0. Generalizing the dust, we can think of that formula. That's only good enough. Because in the rest frame, that gives us that, and we need that. So what do we do? Okay, you follow the logic? What happens here? I define for the dust with a 0 pressure the T mu nu as rho u mu u mu. Okay. Now I know that in the rest frame of a perfect fluid, I have only 2 independent components, T00 Tii, T00 I call it rho, energy density, Tii I call it P. So in the rest frame, T mu nu of a perfect fluid should look like that. Now I'm asking, how is that going to look like? I want to have a general definition which is true in any frame, not just the rest frame. So I'm saying, okay, if I try to generalize what happens with the dust at a 0 pressure. So I used, rather than rho times u mu u nu, I can use rho plus p u mu u. This is a suggestion. If I do that, I end up that in the rest frame I get this tensor, which is not that one. So if I need to get that one, what do I need to do? I need to add to that some other term. What do I need to add?
P times metric.
Exactly. So I need to add minus p, 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 p. This I know what it is. This is p times eta mu nu. The inverse metric because I want to keep up indexes. So overall, I can define, that gives me to define T mu nu as rho plus P u mu u nu plus P eta mu nu. We're going to see that we're going to make a lot of use in that tensor in the course. That's a stress energy tensor. And it's, again, the logic is when you have 0 pressure, we retrieve back T mu nu for the dust. Okay. Non-zero pressure, in the rest frame, this is how the tensor looks like. And this is generally in the frame in which the tensor is not at rest. So if the fluid is not at rest, but the fluid is moving relative to us at some velocity u mu, then that's how the tensor looks. Okay. Now I kind of mentioned it, but I should stress it again. We speak of perfect fluids, but it's not just the thing that comes to my mind, right? You're in the middle of the ocean, everything around you is fluid. But in real life, in astrophysics, everything is a fluid. I can think of fluids, even perfect fluids, as many, many things which you may not be thinking of. Right? The stars are made of fluids. Stars in the galaxy, I can think of them as fluid particles. Galaxies, I can think of fluids. So in cosmology, when we speak about cosmology, we'll say that we can treat this as a fluid. You'll see.
But we can't say that all our universe is perfect.
Yeah, we can't say that.
We can say it?
Approximation. Of course, it's a very good approximation on a big enough scale. We'll talk about that when we get to cosmology. Of course, when you go on a small scale, this is not good. But in a big enough scale, it is a not too bad approximation.
But there is no absolute velocity, right?
Well, we'll get there. Right now, I just defined the stress energy tensor for perfect fluid.
I mean, we don't know where is the rest frame.
Don't worry about cosmology, we'll get there. Due time. I promise you, By the end of this semester, you will know. You will know. Yes.
If I can think of stars in a galaxy as a perfect fluid, what stopped me from saying it's also dust? What's
It
the
is
pressure?
actually less because
Oh, it is.
they don't apply pressure on each other.
But they move in parallel.
Fine, but they don't apply pressure on each other. Dust is a fluid with zero pressure.
Hey, Masaf, what's that word next to dust?
What? Generalizing dust.
Ah,
you
okay,
can
okay.
think of.
Thanks.
So we said just before we go. So I said this T mu nu is symmetric. You can see from here this is symmetric. Why if I change mu and nu, this doesn't care. This doesn't care. So it's symmetric. So one T mu nu is symmetric. 2 T mu nu is conserved. What do I mean by conserved?
Follow the continuous equation.
So conserved means d mu T mu nu is equal to 0. How many equations are here? Are in here?
60.
How many equations do you see here?
4 equations.
There are 4 equations. Right? One is conservation of energy, and 3 would be conservation of momentum, which are Euler's equation. Did you see Euler's equations in any of your courses?
I think so.
Yeah, we said
You're not
waves.
No, Euler's equations for conservation of momentum. Euler did a lot of things. So d mu T mu 0 is conservation of energy. And d mu I is conservation of I momentum. Conservation of ith component of momentum. Okay. Now, last point. I don't know if you've ever thought of that, right? What is rho? What is rho?
Energy density.
Energy density, right? How much energy there is in them. What is P?
Pressure.
Pressure. What's the units of pressure?
I wanted to ask how we can.
What are the units of pressure?
Energy over volume.
The same as energy density. Energy over volume. Okay, I don't know if you've ever seen that, but they have exactly the same units. Think of that. All right. Any further questions? No. Okay, and that's the end of today's lecture. There will be a tutorial on Sunday with Akshay, so be here at 10 a.m. Feel free to ask me questions. You will see me. I just figured out we're going to meet each other again in exactly 3 weeks' time after Passover. Right, so that's some time. I'm going to post up another problem set. Basically, we completed what I wanted to say about special relativity. So the next thing we're going to start to do general relativity. So I'm going to post my lecture notes now online so you can have access to them. But again, don't rely on them. Rely on the textbooks because I gave you the textbooks. So go and read things in the textbooks. Make sure that everything is clear because everything is going to get much more messy than that. And we get to general relativity. I don't want to scare you. I want you to keep constant, be focused, and it's going to get more fun. Hopefully, it's fun for you right now, but it's going to get even more fun. Yes.
Do people use some sort of statistics approach to this problem many particles system? Because we didn't talk.
Right now, we didn't
mention any statistics
we did
and
not
the
need to.
distributions.
We did not need to because we're speaking about perfect fluids. So perfect fluid, everything is, we said, is described by macroscopic quantities such as density and pressure. So I don't need to do statistics. If I'm doing non-perfect fluids, it's a different story. But we're not going to do it here. So the answer is depending on the problem that you have.
So this is like an ideal gas in
Same thing,
thermodynamics, right?
but essentially it's
We have an equation, the equation.
Yeah.
This is it.
It's enough for me to specify the pressure and density
Mm-hmm.
that gives me everything I need. If you want the temperature, there is an equation instead.
This equation fully described.
Yeah. All this for perfect gas, yes. Okay. More questions? No? Again, just make sure that everything is clear in your mind. Right? Alright, so have a nice holiday and come up with new power for the things to come. They're going to be a lot of fun. Alright?
Thank you.